wrapped up last time. Ending on the note of, or talking about bending, introducing the concept of bending loading. Running a different prop today. Bending loading is when the load is transverse to the structure, long skinny structure, loading is sideways, and it creates normal stresses. We don't know how to calculate the stresses yet. We're still just talking about the internal reaction. And we ended up last time talking about the sign convention. Sign convention, very important, because the thing that makes the stress is the internal reaction at a given place. And we started thinking about it as a function of x. How are these changing from one end of the beam to the other? Because it's not the same, depending on where the supports are, depending on where the loads are, those internal reactions are different. So having our sign convention, if we take our section cut and look at either side, either cut face, the internal reactions have to be opposite, because when you put the structure back together, they have to cancel out to equilibrium. And so our sign convention, that an internal bending moment that is in that direction, so if I'm looking at the left face, and it is a right-hand rule positive thing, if I grab onto the end of that and do that, what is that going to make that shape? That's our positive bending moment, and how do you remember that? It's a happy beam. So, we're now going to do another example. We did this, the first one, the simplest of all cases, is the simply supported beam with one concentrated force. We are now going to look at, not that one, where am I? Here we go, page 5. We are going to look at a slightly more complicated case where we have a distributed load over a beam of length L. Now I told you that that W is going to wrinkle some of you guys. W is a weight per length. It's the amount of stuff per length. So if that beam overall weighs 10 pounds and it's 5 feet long, what is W? W is 2 pounds per foot. It's a weight per length. And again, all y'all are going, that makes sense. And I promise in application you're going to goof that up or multiply by 2 or do something weird. Units are your friends. Remember your units. So this is always in a a weight per length is the units. So what's our first step? Always. Free body diagram. Free body diagram of the whole thing to find the reaction forces. We're going to short circuit that just a little bit because this guy's going to be pretty easy, right? It's symmetric, so we know that this reaction has to equal that reaction. And how big does it have to be? Use the fact that we know that this distributed load is W. How big is the overall load? It is not W. It is W times L. W times L. So then therefore, if we have a reaction at A and a reaction at B, reaction at A equals reaction at B equals W times L over 2. Half of the weight is on the left support, half of the weight is on the right support. All right. So now, do we have any discontinuities? When we looked at the one last time, and you have that single force in the middle, you have piecewise continuous functions. We had a discontinuity. Is there a discontinuity anywhere on our domain this time? No. So we're only going to have to make one section cut, and we're going to make our section cut arbitrarily there. And so we need our coordinate system increasing to the right, starting at the left end of the beam. We got our beam. We have our handy dandy reference point O that we're going to use a lot. And we have a distributed load that is of magnitude W. And so that's one of the external forces. We have the external force that is the reaction at A, that is how big? It's WL/2. And then we have our internal reactions. And by sign convention, we have V and M. That V is the one that bothers people because it's downward, but that's the positive convention, again, because of this whole sign convention thing. So now we need to do a statics problem on our little section cut. So we will start with sum of the forces in the y direction equals 0. What do we got? We have a WL/2. We have a minus V. And now how do we contend with that W business? It is of magnitude W times X, and it is minus as well. So it's times whatever arbitrary length we're at our location X. And all that equals 0. We are solving out. We want to know what the shear is as a function of X. So solve this guy for V. And we end up with minus WL/2 minus WX. That's my equation for the shear. Why? Yep. Plus L/2 minus WX. Yep. Typo in the course pack. So be it noted that there's a sign error on page 4-5 of the 4-up filled-in notes. Typo. All right. Sum of the moments about our reference point O. Got to equal 0. I'm actually going to move this over here. Sum of the moments about O equals 0. So if we're using O as our reference point, what do we have? We definitely have a wrong page. We definitely have a plus M. That WL/2 is going to go the other way with what moment on? That's X. So we got a minus WL/2 times our distance X. And then we have to contend with that pesky green distributed load again. So we have to know, and that one's also going to be a plus about O. So we have to deal with the force that it creates, which is W times X. We already established that a second ago. And then what's the line of action of that one? Halfway, X/2. Yes, sir? Okay. So a small amount of algebra moment equals WL/2X
minus w over 2x squared. So that's my moment diagram. So now we got a shear diagram, we got a moment diagram, and we need to plot them. What does that look like as a function of x? Well, we need axes. We'll do the shear first. X increasing to the right. This is shear V. And what does that look like as a function of x? It's our friend slope-intercept form again. So where does it start? It starts at plus WL over 2. So it is WL over 2. And is it going to go uphill or downhill? Downhill with a slope of W. So where is it going to be at x equals L? It will be at minus WL over 2. It's symmetric. It passes through 0 at L over 2, if I could draw appropriately. So at x equals L, it's got a discontinuity equal to the other right reaction force. It passes through 0 at L over 2. And its slope is minus W. All right. So what about the moment M as a function of x? How about your calculus? This guy right here is a very important point. Zero crossing is an important marker when we're talking about that derivative or integral relationship. What does that mean you're going to see down here? A zero crossing means it's an inflection point, or it's a max, it's an extreme, it's a max or a min. How do you know if it's a max or a min? With this slope, here's another new formula. It's almost, I'm almost embarrassed. Slopey down means a frown. You are never going to forget it. So a downward slope means a concave down, so we know that this guy has to correspond to a maxima here. How do I know the value of it? How do I know the value of this guy, of this point down here on the moment? The interval is this. It's the area under the curve for the domain that I have covered thus far. So the area under the curve here for a given ray always corresponds to the magnitude value of this guy. So, what's this area under the red curve? How big is that? 1/2 times base times height. It's a triangle. So, area equals 1/2 times the base, which is L over 2, times the height, which is WL over 2. That's a bunch of 2's. So that ends up being WL squared over 8. So the area of the part that I've scribbled in is WL squared over 8. And we therefore know that that has to be the value at x equals L over 2. It is WL squared over 8. Okay, so we have that anchor point from the fact that we know calculus. We know that it's concave down. And what's the other thing that I have to know? That it has to be true because of boundary conditions. This is where math connects with what you know and understand about the real life world. What happens at the end of this beam? There's no more beam. how much reaction force can be developed where there isn't anything? 0. It has to start and end at 0 because of the physical boundary condition. If there's nothing there, and it's a free end, there can't be any internal reaction, so it has to go to 0 at everywhere. If it's a fixed beam, that's not true. It's a fixed beam, you can have a reaction there, right? You do have a moment reaction. So if you have a fixed cantilever end, that's not true for the moment equation, but if you have a freely supported beam, you will never, the end will always be 0. So therefore, it looks a little sort of kind of something like this. Because how do you know what shape it is? It's a quadratic. You also could have looked at this and went, oh, minus x squared. That's going to be a downhill concave parabola. So that's your moment. That's how your moment changes as a function of x. Internal moment reaction. Internal moment reaction. Cool? Questions? Good? All right. Moving on. Keep it moving. Keep it moving. Oh, what do we got here? We got a cantilever. So, what's the first step? Free body diagram. What do we know? Free body diagram of the whole thing. We know that our reactions are going to end up being a linear reaction at A in Y, a linear reaction in X. There's nothing going on in X, so we can ignore him. And a moment at A. We have a single force with applied magnitude of P, so I know from the sum of the moments about A having to equal 0, I know that the moment reaction at A, which is a plus right-hand rule, minus P times L has to equal 0, which gives me that my moment reaction is in fact equal to PL. And also by inspection or from the fact that the sum of the forces in Y is always 0, I get the fact that how much is my reaction at A? It equals the applied force P. So I have a statics problem on the whole thing to get all of your external reactions as known quantities. Then what do? We got to do this section cut. So section cut, we'll call it there. Again, we have no discontinuities within our beam. And we're looking at what's going on. So we have our section cut. We have our reference point O. We have our coordinate system increasing to the right X. What all is external going on here? We know that we've got my linear support reaction P. We know we've got our moment that is PL. And then we have our internal reactions that are unknowns that we're trying to write equations for V and M. What do we do now? More statics. You thought you were done with statics, right? Every day. Every day I'm staticking. I don't know where these things come from. Sum of the forces in Y is 0. What do I got? I got a plus P minus V equals 0. That one was easy. V equals P. Sum. Wow, that's not legible. Sum of the moments, this time about our reference point O, equals 0. What do we got? Somebody help me out. Who? Plus M. Minus what? Minus PL plus P who? Plus PL? Minus PL. That's that guy. Plus PX. Wait. Here I go again. So, plus PL, this one, and then what is this guy doing? Minus PX. Minus PX. Anything else? What about V? Why? No moment arm. See, you guys are awake. Did I forget anything else? No. All right, what do? We solve this for M. M is a function of X is, get my signs right, this one is minus PL plus PX. All right, what are those going to look like? This is perhaps the most boring shear plot in the world. We have our X. This is our shear V. What does it look like? It looks like a straight line. A straight line with what slope? Zero slope. It's a constant. How big is it? It is that big. Okay, what is that slope? That slope is 0. Okay, if the slope is 0 in the shear, again, you're remembering all of these lovely relationships. If you have 0 slope, what is going to be the slope of the next one down? The slope is going to be constant, so the next plot is going to be linear. If you go from 0 slope in one, you go to a constant slope in the next one. So what do we expect the next one to look like? We expect the next one to look like a line with some non-zero slope. Hey, look, it's a line. What's the slope? Plus P. What's the intercept? Intercept minus PL. So it's an uphill line with slope P that starts at value minus PL. And where does it have to end? How much moment can be out there on that free end of the beam? There's no beam. There's no anything to hold that moment reaction, so it's got to end at 0. And in theory, that's a straight line with slope of plus P. It all jives. It all jives. All right. 0 slope here, constant slope here. Life is good.